Okay, so in DC to DC converter, you have a DC supply, and you want to take a fixed or adjustable DC output from the output of the converter. So the linear regulator is the simplest form of a voltage regulator, where you have this kind of three pin devices: supply, ground, and output. So here you can provide the plus and minus whatever the voltage source. The voltage source can vary. For example, if we take a 12 to 5 regulator, the supply can vary from 15 to 9 volts, but still you will get 5 volts clean output DC voltage. So that's the purpose of having a DC to DC converter. So whatever the supply voltage here, you will get a fixed output DC supply, as well as no matter what type of load you connect, uh, it doesn't change the voltage, and it keeps the voltage fixed at your desired load. So in this lecture, we are going to cover the basic operations of a linear regulator, applications, few application examples, and the efficiency and power losses of linear regulators, and their performance characteristics, and some PCB layout tips essential for PCB layout engineering. Before we move into the linear regulators, let's take a look at what are the voltage regulators. So this is basically covering all the types of voltage regulators, not only limited for linear regulators, but also some other forms of switch mode and other types of voltage regulators. So this video will give you some insight about the voltage regulators and how they operate. So let me play the video.
In the world of electronic circuit design, selection of the right voltage regulator is one of the most important decisions. Virtually every product that runs on DC power employs voltage regulation. But what exactly does this device do? As the name indicates, voltage regulators take variable or unstable input voltages and convert them to higher or lower constant output that matches the voltage and current needs of an electronic circuit. Basic regulators of the linear IC type simply drop down the source to the desired level and shed the rest as heat, while others, such as the switching type, are more efficient. Simply stated, rapidly switching a voltage input on and off results in an averaged voltage output. Depending upon switching frequency, a wide range of voltages are possible from a single source. Some regulators employ additional features capable of handling large voltage spikes, reverse polarity protection, or removing unwanted signal noise. Automotive alternators, as an example, convert mechanical rotational energy of varying RPM into alternating electrical current for use in electrical systems and charging the vehicle's battery. Most alternators employ a built-in AC to DC rectifier and a robust voltage regulator capable of delivering 13.5 to 14.5 volts DC in excess of 100 amps. Each device in the electrical system may have its own voltage regulator depending on its specific needs. Common voltages are 12 volts DC for lighting and accessories and 5 volts DC for sensors and control modules. Linear regulators use a transistor controlled by feedback from a differential amplifier circuit and a reference voltage to control output voltage. They may feature fixed or adjustable output. Output current is determined by the input current minus circuit operation losses. Linear regulators are simple to add and give a fast response time, but are not very efficient. The output of a linear regulator is always lower than the input and drops out if the input voltage is too low. Switching regulators are very efficient but can be difficult to design. As mentioned earlier, switching regulators use controllers to rapidly connect and disconnect either the positive or negative component of the source voltage from the rest of the converter circuit to produce desirable changes in voltage and current. A feedback loop from the output to the controller helps to determine the switching rate. The arrangement of inductors, capacitors, and diodes in basic switching converters determines if the output voltage is increased or decreased. Buck converters reduce voltage. Boost converters increase voltage. Buck boost converters can increase or decrease voltage, but reverse the polarity. Flyback transformers increase voltage to very high levels, but at very low current, by collapsing the field of an energized coil, much like the ignition system in some automobiles. Now that you have an understanding of the basic functionality, types, and common applications of voltage regulators, be sure to check out the vast selection on digikey.com to be.
Okay, I hope everyone got a basic understanding about what is voltage regulators. Now it's time to discuss about linear regulators. So as I mentioned, the linear regulators are the most fundamental and basic forms of voltage regulation. So they have been widely used in industry for a very long time, even in automotive industry or any consumer electronics, portable devices like your laptops, mobile phones, and cameras. Everywhere you can find this kind of small devices step down the voltage. So basically, a linear regulator can't step up the voltage; it's basically step down the voltage to a desired level. So interestingly, step down, but it can step down either positive voltage in positive linear regulators, or you can step down negative voltages using negative linear regulators. So both polarities are possible, but you can't step down a negative voltage using a positive linear regulator, right? That should be kept in mind in the either way. So it was the basics. Linear regulators was the basics for power supply industry until switch mode power supplies came into the market. So they were dominant before 1960, but it's still these software product development engineers are keen to use linear regulators where possible because due to their advantages like fast transient response, low output noise, and high power supply ripple rejection. So typical applications of linear regulators, not limited, but includes industrial power supplies, portable devices, mobile phones, laptops, cameras, force regulation for switch mode power supplies. That is basically when you have this kind of switch mode power supply, or maybe a buck converter. You have this buck converter, high efficiency buck converter, and you can couple a linear regulator. And so the buck converter is, as you know, like it has high noise. So when you feed a buck linear regulator as a pulse regulator, you have this switch mode and then the linear regulator, and this is your output. So you can get a clean and nice output by using linear regulators as pulse regulation. So they are combinedly used with the switch mode power supplies. That's the point that I want to tell. And instrumentation, brushless and brush DC motor drives, and solar inverters. In this example, we can see here we have a typical portable device management system. We have a single battery source. The battery voltage can be 4.2 when it is fully charged, or can be dropped to 3.1 when the battery drives out, when it is required for charging again, right? So the voltage range of the battery could vary from 3 to 4.2. And different peripherals of the portable device in your mobile phone, for example, could be USB, analog, processor, memory card, modem, and Bluetooth modem. So these kind of devices require different voltage rails to operate. So in order to satisfy the requirement, so you can couple linear regulators. So the linear load power regulator types, I will discuss what is LTO regulators. So this kind of portable devices, in order to get multiple output voltages, you can use linear regulators. But the problem is they having some other disadvantages, like they are low efficiency. If the power efficiency is not ideal, and your input and output voltage difference is very much close to each other, by using a LDO regulator, you can estimate power management system using linear regulators. Right. So we can have this simple example. We have this in order to understand the concept of a voltage regulator or the concept of a linear regulator. I have sent you this example to work by yourself. Hope you have worked by yourself. So in this example, just I want to show you is we have this load, could be a light bulb, and we have this 12 supply, and we have this 1K resistor. And all we need to have is 5-volt output at this load, right? So we can just find by using this resistor divider rule. By using this resistor divider rule, the just want to tell you. All right, back to the class. Here we have resistor divider. When there's no load, we can have a 5-volt output. So in order to satisfy this 5-volt at no load, so we can calculate this R resistance. If anyone has calculated this value, just type in your chat box so we can just right. So 1,400 ohms. Yeah, that sounds good. Yeah, that should be actually kilo ohms. Yeah, this is kilo ohms. Sorry for that. So the next value is when we just switch on this device. Let me just correct this. So when you turn this on, right? So this is the load also has a resistance of 1K, and so this total resistance drops to 0.5K, right? Equivalent resistance. So if you have this value 1.4K here, you will get a different voltage, right? So that value, how about that value? The second one. So when you load this one, what will you get? Anyone got the answer for the second one? Right, if you're done correctly, you should get 3.16 volts here. And likewise, you can, so load value is shown here 1K, right? So load resistance is 1 kilo. And right, so interestingly, what you want to do is if you use this resistor divider, the output voltage at no loads, you can, for this value that you calculated at 5 volts, but when you load, the voltage drops to 3.16. So you can again change this R value to, in order to satisfy this load requirement, you can change this value. You can find this value. And again, right, so everything will be run smoothly. You have your recalculated R here, so you get 5 volts when you load it. But what will happen when you increase this supply volt to 13 volt? Again, your output will be changed, right? So you have to again find a new value for R if the supply voltage goes to 30. Right, that's the limitation of this kind of resistor divider based concept. In order to overcome this problem, what we can simply do is we can make a mechanism that someone can adjust this resistor by looking at this output voltage. So this, we want this as 5 volt. If it drops, you can change this resistance. If it increases, you can adjust this resistance until you get 5 volt. That is the basic concept of a linear regulator. You have this your load, and you have this variable resistor, and there's a mechanism we change this resistor depending on the load, changes in the load, as well as the changes in the supply voltage. Right. So discuss the limitation of this circuit to keep fixed output voltage against the variation of load and source voltage. Basically, it can't provide a fixed output voltage due to the changes in the supply voltage as well as the loading. So what other factors can affect the regulation of the output voltage? So anyone has, so I have mentioned the output voltage could change with the supply voltage changes as well as your output load type. What other factors can affect the voltage regulation? Anyone can type the answer for this one, other factors? Yeah, one factor is the temperature changes. Based on the temperature fluctuations, this even if you do this one, the resistance will change. So you have to compensate that issues as well. And also, if there is some noise comes from this source, you have to eliminate and filter it out from your regulator. So in order to make a clean supply voltage. So those are the basic other factors other than your supply voltage and load. Right. So this slide shows you the basic operation of a linear regulator. And like I mentioned, we need a feedback loop to adjust this R resistance. This is your load. And we just monitor this output voltage, and based on the changes in the output voltage to any factor in the supply voltage or load or any other temperature fluctuations, so we adjust this R value. So we need to have this feedback loop. And so this is the basic concept. So this variable resistor, I will show you what is that looks like. And this is the concept of a linear regulator, and this is what is really implemented inside the linear regulator. So as a variable resistor, you can use a transistor or MOSFET running in this amplifier mode, not as a switch or not as a switch, but in the amplifier mode, you can change the voltage across it based on the current. So that means like it acts as a variable resistance. Based on the, if it is a transistor, you can change the IB current. If it is a MOSFET, you can change the gate to source voltage in order to change this resistance, right? And in order to get this control loop, we can have a resistor divider and this comparator, and it compare with the fixed reference voltage, your desired value, desired output. If it is 5 volt, you can keep your reference as 5 volt. Or if you use a resistor divider, depending on the ratio, you can use a reference voltage adjusted to the value that you want. And so this error amplifier will change its gate current or gate source voltage based on your pass transistor and regulate the output voltage. So this is the basic concept of a linear regulator. You need to have feedback loop. It's a control. This is a P-type controller, just error amplifier, and this is your control signal. So everything is analog. There's no digital parts required. In linear regulators could be analog or digital, but in this lecture we're just covering the analog ones. So it's very simple. You can have your pass transistor or pass MOSFET here, and by controlling its gate voltage or gate current, you can control this resistance. Right, linear regulators could come as different types. The most common one is fixed output linear regulators. So they are just made with 3-pin devices as supply, 3 pins, one for supply, one for ground, and one for output. Sometimes The ground pin could be adjustable in adjustable linear regulators, but basically has 3 pins. So this is the basic form of a linear regulator. 3 pins are connected in such a way. You have this input, ground pin, and the output where you connect your load here. So additional capacitors might be required for filtering and stability. The most widely used one you might have seen, the LM7805, the 5-volt output linear regulator from Texas Instrument. You can step down any voltage from 12 to at least 7 volts. You can get a 5-volt output. The input voltage source can, in this one, could be the maximum up to 35 volts. If you provide 35 volts, still it will provide 5 volts. And the minimum value could be around 7 volts, as I could remember. You can't step down up to 6 or below than 7, it won't work. And the temperature range is this, minus 65 to 150 degrees, and load current could be from 0 to 1.5 amps. Right. Now, the other version is the adjustable output linear regulators. So adjustable outputs has, you can change the output voltage, like a benchtop power supply. You have seen you want adjustable output, whatever the supply voltage here. So in this case, the ground pin is known as the adjustable pin. Still, this is a 3-pin device. The pin number 1 is the adjustable pin. You have this 2 resistors. By changing the R2 value, you can change the output voltage. So in adjustable versions, you have to have this additional output resistors. In the previous one, you don't need this feedback loop. Here, your feedback loop is connected outside to the linear regulator, so you have to add this resistance outside the linear regulator. So you have to use these capacitors based on the requirement. For example, now if you buy a adjustable linear regulator like LM317, if you want a fixed output, let's say like you want to build a, you have this device and you want to get 3.3 volt output. So you can find this R1 and R2 values, finding the manufacturer specified equation. So you need to know your desired output value, and typically you can take one resistor to a known value like R1. You can assume the manufacturer sometimes specify this, what is R1, 240. You can substitute that value here. And I adjustable is also given in the data sheet. It's around less than 100 microampere, so you can use any value. And then you can find this unknown value R2. Then you can build whatever the voltage you require at the output. So it's very simple steps. We will work on an example in later. That was all about the positive linear regulators, but also there are common type is negative output regulation type linear regulators. So they will step down negative voltages. So they can come either adjustable or fixed output. This example will show you a adjustable negative output supply. Here you can see now the supply pin is negative voltage, is connected to a negative supply, and you have your adjustable pin connected to a feedback network and connected to the ground, and you can get your negative output, regulated negative output from this pin. So you might have some input capacitors and output capacitors, and you can step down this negative voltage to your desired value. So this LM3370 is a negative adjustable type linear regulators from Texas Instrument, which can provide you 1.5 current at the output. So there's a concept called the quiescent current of a linear regulator, which is the this current goes from this ground pin. That is, we want to just take a look at what is that quiescent current is. from this video.
A common issue in modern electronics is picking up an electronic device that you've barely used, only to find that the battery is nearly or completely dead. If your device was just on standby or sleep mode, this may have happened because of a small but crucial specification, quiescent current. In today's video, we will explore what exactly quiescent current is and how it may affect your LDO and your electronics. Let's begin. Quiescent is defined as a state or period of inactivity or dormancy. Thus, quiescent current, or IQ, is the current drawn by a system in standby mode with light or no load. Quiescent current is commonly confused with shutdown current, which is the current drawn when the device is turned off but the battery is still connected to the system. Nevertheless, both specifications are important in any battery application. Now that we know what IQ is, we can delve a little deeper on how it actually affects an LDO. The first thing that should be considered is how much power is being dissipated through the LDO when the device is active and how much power is being dissipated when the LDO is in standby mode. The equation below is the power dissipation equation for an LDO. The total dissipated power is equal to the input voltage minus the output voltage multiplied by the output current, plus the input voltage multiplied by the quiescent current. Now that we have the power dissipation equation of an LDO, let's use an example to see how it may affect an application. For this example, we'll be using a 4.2 volt input from a battery that will be regulating 1.8 volt, 200 milliamps of output current, and 50 microamps of quiescent current. We plug those numbers into the equation, we get this, and a total power dissipation of 480.21 milliwatts. Now this is when the device is active. What happens when the application switches to standby mode, where quiescent current plays a much greater role in power dissipation? Let us say that the output current while in standby mode is 100 microamps. The dissipated power becomes 0.45 milliwatts. In this example, quiescent current contributes to nearly 50% of the power dissipated. Now, you're probably thinking, well, that's not that much power being wasted. What about applications that spend a majority of their time in standby or shutdown mode? Applications such as smartwatches, fitness trackers, and other types of wearable electronics frequently spend their time in either of those states. This means that the IQ of the LDO used for regulation plays a significant role in battery life. Something else to consider is also the size of the LDO. We've come a long way from having these huge linear regulators from 60 years ago to these ultra small wafer chip scale packages. We can see that this also matches the continuing trend in electronics of smaller and lighter products. This is because in these consumer products, the battery is usually the largest and heaviest part of the design. However, designers don't want to typically shrink the battery because that would decrease both the capacity and lifetime of the battery. Therefore, it's critical to keep all other onboard devices as small as possible while maintaining performance. TI has LDOs with peak power performance and a small size because thermals aren't a huge issue for low power dissipation. The TPS-7805 is a prime example. It boasts a 0.65 by 0.65 wafer chip scale package with 0.35 millimeter pitch that provides a 1 microamp of quiescent current. For those who don't need that size, the TPS-7805 is also made in a 1x1 quad flat no lead package. This not only makes this device one of the smallest sized LDOs, but also one of the lowest IQ devices on the market, giving you the best of both worlds in terms of size and performance. An enable or shutdown pen is another simple solution if you're designing to conserve battery life. Smartwatches, fitness trackers, phones, and even drones can employ the solution for a battery boost. Drones, out of all the consumer electronics that were mentioned, spend very little time in standby mode because they're usually only idle pre or post flight. However, you can still save battery life by shutting down LDOs attached to those modules not needed for flight. A good example for these modules are the image sensor, as this is only needed when the user wants to record videos or take photos. Since this module is off, the shutdown current is the only drain on the battery, which is even lower than the LDO's quiescent current. Although battery life is highly dependent on the load conditions while running, LDOs with low quiescent current are a simple solution to help boost the runtime of any battery-driven device. These small devices are not just limited to consumer electronics either. They play just as big of a role in industrial applications such as smart meters, building, and factory automation. So even though designers sometimes overlook quiescent current, they can ultimately make the difference in an application running for a few more seconds to days or even years. Now that you've learned the importance of quiescent current, make sure to always account for it in your power dissipation calculations.
Okay, now you have idea about the importance of the quiescent current. So in this example, I have shown you the uh, linear regulator or LTO type, a lower power regulator. I will explain what is LTO in just in a minute. So the linear regulator, in order to work, so you have this input current and this quiescent current following through this ground pin and your load current. Basically, following the Kirchhoff laws, whatever the input current should be equals to the quiescent current plus your output current, right? Whatever the current enters should be equals to the current left. This plus and this plus should be equals to input current. So this internally it has this variable resistor or your series pass device. It dissipates the energy by adjusting its resistance. So that is the fundamental component. You have this variable resistor, but you have also seen some control devices such as op-amps, reference source, and feedback resistors. They also, your control circuit also requires some sort of power, right? It takes this power from this whatever the current comes, your control circuit is here. It is connected to this ground pin. So this internal circuit consists of these devices will consume power, right? That also count for energy loss, because the lower this quiescent current is, which means your control circuit consumes the lowest current, so your system is more efficient. So that power loss due to this quiescent current is simply your supply voltage into your quiescent current. So in typically, like in the previous examples for the drones or portable devices or consumable electronics, so it is really essential to keep this quiescent current as low as possible by reducing the size of the LTO and using more electronics as small. I mean, designing this part to keep the lowest quiescent current will enable you to save your battery life here. That is, the control circuit requires the power, so we have to reduce this control circuit power as possible, as low as possible. But that is very small portion compared to the heat dissipation across this variable resistor, right? This quiescent current is essential because when you just need your load sometimes enable the load or disable the load. There are some pin called enable in the LDOs. So in the standby mode, you can disable your output, and then it is only consuming this. The power is consumed via this control circuit. When you enable this one, so your load is getting power. So in the standby mode, so typically you disable your output. Then the control circuit consumes power. So when you have low power consumption in your control circuit, you can save the power. So that is one sort of power loss in a linear regulator, but the most of the heat is dissipated across this series pass device or the variable resistor. So the total power loss is given in this equation. That is, the power loss across this resistor. So this voltage is V out and this voltage is V in. So the voltage difference across this resistor is V in minus V out. This is that voltage difference multiplied by this current, because some part of the current goes through this ground pin and other part goes through this resistor. So that is equivalent to the load current. So when this is the power loss across this resistor. So we know this voltage drop and we know the current passing through the resistor. Applying V is equals to VI, you can get the heat dissipation through this resistor. Plus the control circuit current. That is simply this voltage into the quiescent current will give you the power loss of the control circuit. So both factors will govern, but this is the major part of the power loss. So that leads for more heat dissipation of the pass device. But when it is in the standby mode, only the control circuit consumes the power, which means there's no, the load is disabled. So the efficiency, simply we can find the efficiencies, that is the ratio of output power to the input power. So the output power is what is the power that you've taken from your load. That is the output voltage into the output current. This is your load power or desired power, and this is your input power. That is this voltage into this current. And if you're having more losses in your linear regulator, the efficiency goes down. If the losses are can be minimized, you can have the system more efficient. This is the fundamental equation, but we can get an approximation assuming that in a well-designed linear regulator, the quiescent current is approximately, you can take it as 0, a well-designed one, right? So in that case, we know that I out should be equals to I in, because this IQ is, when IQ is 0, I in is equals to I out. So from there, so these two parts get cancelled. So you can take the approximation as the efficiency is simply ratio of output voltage to input voltage, assuming the quiescent current is very low. But that is valid for well-designed linear regulators when the quiescent current is very small. I hope this concept is clear for you. Now, this is the interesting part. So the linear regulators, there's one member of this family, which is called the low dropout regulators. So they are more efficient compared to the typical linear regulators, because according to this equation, the efficiency is the ratio is into the input to the output. So typically, if you design your linear regulator, get this V in very, run this V out and very close to V in, you can get the efficiency as close as to 1, right? So in normal linear regulator, you can't get that value because there's a voltage drop always across the series pass device that is significant, typically 2 volts, right? In that case, you can't never get V out close to V in, but low dropout regulators, this voltage drop could be dropped to around even 0.1 volt. That kind of a small voltage drop, which means that your output and input is almost same. You can run your system with the efficiency greater than 90. So that can't be done in simple arrangement. So most of the time, this kind of LDOs are built with PMOS or NMOS transistors. One example is this LM, the linear regulators I explained, they require at least 7.5 volts to regulate 5 volt, which means 2.5 voltage drop across the device. But this kind of LDO regulators, they only take 100 millivolt drop across this one in order to regulate. Ideal for post regulations with switch mode power supplies to run a very efficient system. But the case is that the theory is, so let's take this one is 3.3 volts. And so you can run your system even at 3.4 volts. If you have 3.3 volt, this will do the regulation. If you drop to 3.35 volts, the output will not be 3.3. It will not regulate. It maybe goes to 3.35 volts. So the input voltage should be greater than to the supply output voltage plus your this dropout voltage, right? Then only any linear regulator works. For this kind of LDOs, that drop is very low. The other types of linear regulators, like old-fashioned LM785, to get 5 volt output, you have to keep at least 7.5 at the input to get the regulation. If this voltage drops to 6 volt, you won't get 5 volt. Maybe your voltage will drops to 4.5 volts, because they are not low dropout. Low dropout means you drop out this the voltage drop across the device is very low. V is very low. So this video will discuss you the basics of the LDO. Let's watch this one first.
In this video, we'll be going over the definition of an LDO and the importance of dropout voltage, as well as explaining the conditions that can affect this parameter. So let's start with the most important question of the day. What is an LDO? A low dropout regulator, or LDO, is a DC linear voltage device that can regulate even when the supply voltage is close to the output, i.e. low drop. During regulation, the voltage output will be determined by the voltage input and the dropout, as can be seen in this formula. In the example on the right, we have a 5 volt input going into our LDO, the TLV760, and our output is internally set for 3.3 volts. Therefore, our drop voltage is 1.7 volts. The power from the voltage differential will then be dissipated as heat from the LDO. We will explain the dynamics of heat exchange in a later video, but for now let's focus on the voltage dropout, as it is the quintessential characteristic of an LDO. It is also important to note that while the voltage drop here is 1.7 volts, this is not what we consider an LDO's voltage dropout. Voltage dropout, usually represented as VDO, refers to the minimum voltage differential needed between the voltage input and the nominal voltage output to maintain regulation. Therefore, in order to maintain a desired output, we must ensure that the input voltage is at least the desired nominal output plus the minimum voltage dropout of the LDO, as can be seen in the first formula. Should the voltage input fall below this value, the LDO will enter dropout regulation and will not be able to yield the desired output. In this case, the output voltage will track the voltage input minus the dropout voltage, as the formula shows. As an example, consider an LDO like the TPS799, as shown on the right. We picked this LDO because it has a fixed 3.3 volt output we can leverage. If we look at the datasheet, we can determine that this LDO's maximum dropout voltage is specified at 175 millivolts for a current output of 200 milliamps. Let's now assume that the input voltage drops to 3.375 volts. Referring to our previous formula, our LDO will now enter dropout operation, and the resulting output would be 3.2 volts instead of 3.3 volts. If we wish to ensure proper regulation here, we must at least use 3.475 volts. As you can see, dropout is one of, if not the most important parameter for an LDO. So let's take a look at what determines the dropout for an LDO. The architecture of an LDO is a primary determining factor for dropout. To see why, let's compare an NMOS-based LDO to a PMOS-based LDO. On the left, you can see a typical PMOS LDO architecture. In order to regulate the desired output, the feedback loop controls the drain to source resistance, or RDS. Because P MOSFETs work with a negative gate to source voltage, or VGS, the higher the input voltage, the more negative VGS becomes, and therefore a lower RDS is achieved, directly reducing our dropout. The dropout is proportional to the current output, but for this comparison, we will treat it as a constant. In the case of an NMOS architecture, the feedback loop will still control the RDS. However, NMOSFETs work with a positive VGS. Therefore, the error amplifier will try to increase the gate voltage to ensure this operation. When the error amplifier saturates, it will not be able to reach a higher voltage than Vin. This prevents ultra-low dropout operation. In order to reduce the dropout needed, we can also reduce the output voltage. But how can we solve the problem of low dropout in an NMOS? By using architectures with a bias pin or internal charge pump, we can effectively increase the voltage for the error amplifier, thus achieving a high VGS without the constraints of the input voltage. This can ensure that an NMOS architecture also has a lower dropout. Here are other variables that can affect the dropout of an LDO. As we discussed, the main one is architecture, but the size of the pass element or FET will also affect the dropout. A larger size FET will yield a lower dropout. Output current and temperature also affect dropout. As both increase, so too will the dropout. It's clear that dropout is not a static value, but rather than complicating your LDO choice, these variables should help you choose the optimal LDO for your specific conditions. When designing your circuit, be sure to keep an eye out for the conditions in the table and keep track of the input voltage variance. Any changes there could potentially change how the LDO regulates.
Okay, now it's time to work on a simple example. Here we have this power loss calculation example. So just work by yourself. The example is here. Calculate the efficiency of this TPS LTO regulator. So the output voltage is 3.3 volts, and the input voltage is set to 4.5 volts, and the output current is the maximum current is 100 milliamp. The maximum quiescent current is 17 milliampere, right? So the efficiency, it is asking what is the efficiency. So you know, the efficiency is simply input output power divided by the input power. Right, this is the equation of efficiency. So what is the value of the output power? Output power is simply, we know the output voltage is 3.3 volts and the output current is 100 milliamp. So you can calculate the output power using the product of this one into this current, right? That is your output power. And the input power is simply the input current voltage into the so this is the LDO, and this is the ground. So this is IQ, and this is I out, that is goes to your load, and this is V in, and this is I in. So we just know the P out now. The P out is very simple. P out is simply this current into this voltage, right? So the input power, so the input voltage we know, this is 4.5 volts, and the power, so the we just need to know what is this I in current, right? I in current is simply the IQ plus the I out. because whatever the current enters should leave. So IQ, we know that is 17 milliamps. I out, we know 100 milliamps. So by substituting these values to the input power, you can get the efficiency, right? So it is very simple. You can work by yourself. And the power dissipation of the LDO is the total power loss across this resistor as well as your control circuit. So you can use simply this equation here. Right, this equation here. The power loss is difference between the input and output voltages into the output load plus the quiescent current into the supply voltage will provides you the heat dissipation across the linear regulator. The efficiency is simply the output voltage into output current divided by supply voltage into the supply current. Supply current is simply, if you know the IQ and I out, you can just get the summation and get this efficiency. So it is very simple calculation. I hope everyone can work on this, and I'll let you guys 10 minutes break. Note down this one and get the values, and we will start the session around 10:45. Okay, so get your answers and put on the chat box. So if you want this slide, take a screenshot, or I will upload this presentation just in a minute. Let me share you the PDF so it will be easy. Okay, I hope you have seen the example how I worked out on this one. So simply the answers are for the efficiencies around 62.6 and the power loss is 0.1965 watts. All right, so we move to the next one. So from this slide onwards, we are looking at the performance characteristics of a linear regulator. So the first one is the line regulation. Line regulation is when you change, so you can change your input supply. You can vary the supply, for example, from 5.4 up to 6.6, and you can plot your output voltage, right? And in this example, you can see for different load currents, output load, the output voltage is plot against your supply voltage. In ideal scenario, this should be a flat line. No matter whatever the supply voltage or the load current, you should get a 5 volts fixed output voltage. But as you could see here, when the load current increases, your output voltage deviates from its required value. 5 volts is desired, but it can reduce. So the line regulation is a performance characteristic of a linear regulator. So that is defined as the change of the output voltage for the given small change in the output voltage to a change of the input voltage, right? So if you here you can see there's a slope, which means a very bad line regulation. If you have a flat line, which means the linear regulator has a very good line regulation characteristic. So you have to worry about keep an eye when you buy a linear regulator. What is the line regulation? Which is very, if it is very low, which means no matter the load current or the supply voltage changes. For example, for any given current, when you change the supply voltage, the change in your output voltage is minimal. That is any design engineer looking forward. So whatever you change in the supply voltage, you should get a very low change in your output voltage. So that parameter is defined in data sheets. It's a ratio of a change in the output voltage, the ratio to the change of the output voltage to the change in the input supply. The lower the line regulation, the better. So the line regulation can decreases with the increase of the load current, right? It will get worse. The other characteristic is the load regulation. Load regulation, here you fix your supply voltage to any value and you change your load. So from no load current, very light load to your maximum load current, you can change your load current and you can plot your output voltage. So as you could see here in the for lower load current, so the output is almost 5 volts. But when you when the load current increases, the output voltage deviates from its desired value. So this is really bad. But if you work in this, the load current in this region, you can work without an issue. But if you are working here, you can see when your load current is nearly 2 ampere, the output voltage has dropped around 4.95 volts, very to a slightly low value. So the load regulation is a measure of its performance. It's the change of the output voltage to a change of the load current, right? Finally, we have this power supply ripple rejection, which is also known as PSRR. That is simply in our standard diode example also I have explained you. So LDO regulators does not directly connected to typically connected to switch mode power supplies in post regulation, as I mentioned, because due to their high ripple rejection. So when you build efficient power converters, you might have multiple voltage regulation stages. So at the post regulation, which is where you connect your load by connecting a LDO regulator, you can get rid of any noise coming from the upper streams voltage regulators like switch mode power supplies, and while you can keep a very nice and clean output supply. So the power supply ripple rejection ratio is the output voltage ripple appearing at the output side to the ratio of the input side. So if you have higher PSRR, which means this LDO or the linear regulator can suppress more noise and keep your output side noise-free voltage regulation. This example shows you that PSR is a frequency-dependent characteristic, which means the PSR depends on the frequency. So you have to plot the PSR against the frequency. Here, this example shows you the PSR of a LDO regulator. So this axis shows you the frequency, and this is the amount of ripple rejection in decibels, right? So ratio of output ripple to the input ripple and getting the decibel value. Here you can see at different, it's not mentioned what is this, could be typically the dropout voltage. Right, so as you can see here, for low frequencies, the ripple rejection is high. When the frequency increases, the ripple rejection, the value of ripple rejection goes low. Which means if you're getting a noise at this frequency around 10 megahertz, the ripple rejection is very low, you can still get some noise. But if your noise is in this region, you have high ripple rejection, which means you will get very low ripple, right? That is the concept of power supply ripple rejection. If you're worried about any noise coming from this input side of any power supply in automotive application or any consumable electronics or any industrial application, if you want to suppress, and if you know the frequency of this ripple by purchasing a LDO regulator and looking at this PSRR characteristics, and based on this frequency and the PSRR, you can get rid of that noise. Most of the time, when you buy a high PSR regulator, you can eliminate any noise coming from this source side. The supply source is always noisy. By using a high PSR linear regulator, you can keep your noise level to a very low value. So this video will demonstrate you the PSR in details. So let's.
In today's video, we'll be going over power supply rejection ratio, otherwise known as PSRR, and why the ability to attenuate voltage ripple generated by switch mode power supplies is one of the most touted benefits of low dropout regulators, or LDOs. Let's begin. So what exactly is PSRR? PSRR is the degree to which an AC element, usually a voltage generated from a switch mode power supply of a certain frequency, is attenuated from the input to the output of the LDO. In other words, it determines how much noise from the input couples into the output. This ratio can be expressed as the following equation. PSRR is equal to 20 multiplied by the log of the input voltage ripple over the output voltage ripple. This equation also tells you that the higher the attenuation, the higher the PSRR value is in decibel. Using the following high-level block diagram as an example, the DC to DC converter introduces switching noise, which is conducted via the line. There may also be radiated noise that is being conducted at the input as well. When following the arrows, we see that the LDO will then reject some of the noise that was generated before adding some internal radiated noise. The resultant signal will then be a clean DC signal with minimal ripple. We will now go over how to determine PSRR in your application. In this example, we will use figure 1, which shows a DC to DC converter that is regulating 4.3 volts from a 12 volt rail. For the LDO, TPS717, a high PSRR LDO, will follow the DC to DC converter by regulating a 3.3 volt rail. The goal of having a high PSRR on an LDO is to get a flat DC signal at the output of the TPS717. The ripple being generated is 50 millivolts on the 4.3 rail on the output of the DC to DC converter. The PSRR of the LDO will determine the amount of ripple remaining at the output of the TPS717. In order to determine the degree of attenuation, you first need to know at which frequency the ripple is occurring. For this example, let's assume 1 MHz. It is common to find the PSRR value specified on the datasheet under the electrical characteristics table. As you can see, the value for the PSRR at 1 MHz is 45. It is important to note that these values only apply under these conditions, which means the PSRR values may be different under different conditions. Another way to determine the PSRR is to consult the PSRR versus frequency plot that can be found on the datasheet. This particular graph is for the TPS717 with a delta between Vin and Vout of 1 volt. Now, assuming that these conditions match your own, your PSRR value will be 45 decibels. Now, using equation 1, you can then solve for your attenuation factor, which in this case would be 178. This means that you can expect the 50 millivolt ripple at the input to be reduced down to 281 microvolts at the output. But let's say that you changed the conditions and decided to reduce your Vin to Vout delta to 250 millivolts in order to regulate more efficiently. We would then have to consult figure 3. You can see that if we hold all other conditions constant, the PSRR at 1 MHz is reduced to 23 decibels, or an attenuation factor of 14. This is due to the fact that the CMOS pass element is entering the triode, or linear region. Or in other words, as the Vin to Vout delta approaches the dropout voltage, PSRR begins to degrade. Now, please bear in mind that dropout voltage is a function of output current among other factors. Hence, a lower output current decreases the dropout voltage and helps improve PSRR. Changing the output capacitor will also have implications as well, as shown in figure 4. By increasing the output capacitor from 1 microfarad to 10 microfarad, the PSRR at 1 MHz increases to 42 decibels, despite the Vin to Vout delta remaining at 250 millivolts. When we compare the two plots, you can see that the high frequency hump in the curve has shifted to the left. This is due to the impedance characteristics of the output capacitors. Now, by sizing the output capacitor appropriately, you can tune the attenuation to coincide with a particular switching noise frequency. Now we've seen that by adjusting the Vin to Vout delta and the output capacitance, we can improve PSRR for a particular application. These are by no means the only variables affecting PSRR. As you can see, the table shown outlines other various factors that come into play. For instance, Using the last example, changing the output capacitance will have little to no effect at lower frequencies, but has an impact at higher frequencies. Whereas changing the noise reduction capacitor will have no effect on higher frequencies, will have a major impact on lower frequencies. To learn more about PSRR parameters such as feed-forward capacitors or PCB layout, please refer to our additional resources that refer to other blog posts and application notes that go into more detail regarding the various parameters that affect PSRR.
Right. So you just need to know is that PSR is not a fixed parameter. So it depends on the operating condition, the output current and dropout voltage, and even the capacitance of the output capacitor you're connected, and your PCB layout also affect the PSR. So considering all this, even the datasheet show you a nice graph based on the some characteristics for given test setup, but there could be some other factors which affect the PSR as well. So you have to keep in mind these parameters should be taken into account when you design your power supply for low noise applications. Right. So linear regulators or LTO types is always in nature they are unstable. So which means you have to make them stable. So there's a control loop. So that control loop should be unstable. So in order to make the control loop stable, you have to add this output capacitor and change the equivalent series resistance to the desired level. Otherwise, the output will be unstable supply. So what will happen if the unstable supply, if he doesn't make this regulator stable by using this capacitor? So in this example, you can see, right. First, I will explain the concept. So you need to have this output capacitor equivalent series resistance within the desired level in order to make your regulator stable. That is basically control theory part. We are not covering that one. So that is changing the poles and changing the zeros of this control loop in the open loop transfer function. So that will add more phase margin. So that is out of the scope. All you need to know is by using this ESR to a desired level, you can keep this control loop stable. So the ESR range is typically defined in the manufacturer data sheet, and that is called the tunnel of death characteristics. This is a typical example from TPS 7633 datasheet. So based on your output capacitance, they have recommended to use 4.7 microfarad output capacitor, and the ESR should be within this range in order to make your system stable for different load currents. In order to, if your regulator is working all the load current range from 0 to 250, your ESR should be in this region. If you select a 1 ohm ESR value for the capacitor, typically you can't, when you bind the capacitors, the ESR is mentioned, so you have to check with your datasheet, the capacitor datasheet, what is the ESR value. So if your selected capacitor has a 1 ohm, so you know your whatever the load current that you connect here, your system is stable. If you pick, for example, let's say a value here, around 10 ohm resistance for ESR, and so it is stable only the current less than around 70 milliamps. So if the load current increases to this range, you will get unstable, right? So you have to keep in mind this is the stable range of the ESR. So your capacitance should be enough to there. So one practical example I have seen when I was working on the regulators, one day I forget to add this output capacitor. And when I observe the output voltage using oscilloscope, I want nice and clean 5 volt here. But instead, what I saw was something like this. It is really control system, unstable system, right? And this is what will happen if you put the ESR out of the range. So as you can see, you can change your load current from 0 to 250. Just you can switch on your load, right? And if you use the ESR within this range, the 1 ohm, the output voltage will be just slightly drop and come back to the normal the 5-volt range. But if you use unstable ESR, either it is very low or very high value. In this example, it is very low value. If you change your load from low value to high value or vice versa, this is what your output looks like. It's oscillate. It's an unstable system, right? So you might think like LDOs are very simple device. You have this input and output and ground pin. But if you doesn't pick your ESR to the right value using this table, you will end up with a very bad system. You won't get any regulation, right? So always look at the manufacturer's specifications and select your ESR value for the capacitance. So they also refer different capacitors, solid tantalum electrolytic, aluminum electrolytic, or multi-layer ceramic. Most of the applications, when I was working for my projects, I always use multi-layer ceramic capacitors and X7R series, which means it has more temperature, very low temperature variations. So like the capacitance and the ESR also changes with the temperature, right? So even if you pick 4.7 microfarad at room temperature, and the ESR is 1 ohm at room temperature, but when you're running, the LDO get heat up and this temperature increases, the ESR might be drops or increases, maybe increase to a value. If that, due to this temperature range, if it jumps to the out of the instability region, the ESR changes, it jumps due to this capacitor characteristic. It will be a very bad design. So always keep in mind, use when you're picking your capacitors with the desired ESR, take a look at the temperature fluctuations and other environmental factors as well. Sometimes the ESR will change upon this DC voltages and several other factors. Most of the time, the ceramic multi-layer capacitors are more suitable than aluminum electronics or tantalum electrolytic capacitors are also used, but they are very expensive. This is the most cheap and the best solution using these ceramic capacitors. Right. Okay, now we are moving to a example. Before that, I will show you one other factor. This is the recommended layout of a LDO regulator, right? So this LDO regulator has this package, and the footprint looks like this. And these are your ceramic capacitors, SMT type, and your feedback resistors if you're using an adjustable resistor. So typically, that this internally this is dissipating heat due to this internal series pass device. That heat should be coupled to this pad, but sometimes you might need to use a heat sink. But most of the applications, by using a copper plane, you can dissipate more heat to the copper plane. So in my double layer PCBs, you can have this top layer filled with copper pore, and having some, and also you can make an additional copper layer on the other side, and you can put some thermal vias, so that will transfer the heat of this device to the top plane, and from the top plane it will dissipate to the other outside. And this thermal vias also transfer the heat from the top layer to the ground, and from the bottom layer also it will dissipate heat. So which means your equivalent area is increased now. Also, it will give some thermal relief when you're soldering your device this pad, right? So if you don't manage your thermal behavior or this heat dissipation of this device, the LDO will heat up. If it heat ups to the maximum value, if the internal die temperature increases, the LDO will fail. So it will collapse. To overheated, then it will collapse. So just selecting the right area for this copper core and adding number of thermal VRs and heat sinking is the job role of a typical electronics engineer. But that should needs more skills. This is out of the scope, but remember, by adding copper pores and thermal VRs, you can get rid of the heat and keep your device cooler without exceeding its temperature. And so you have seen this input and output capacitors. They should be very close to the device. You can't keep this input capacitor somewhere here, right? If you add, it will degrade the performance. And also you have to keep your output capacitor very close to the device output pin. For example, now you know the output capacitor, this ceramic multi-layer capacitor is like this. It also has some small, the inductance is very small, but it has this ESR and this capacitor. So when you keep your capacitance very close to there, you can get the desired response. But if you put this output capacitor somewhere here, far away from your, I mean, this is your load. You can put your output capacitor very close to the load rather than close to your device. What will happen is, so this is connected via PCB track. The PCB track has the inductance and equivalent resistance, right? So you select this as one node from the datasheet, that is your stable ESR. But due to this longer wires or any other things, so this will add more resistance. So now the equivalent ESR becomes 2 ohms. So that might be out of your stable range specified by the manufacturer. So you will get some oscillations, right? And also the inductance also affect. Therefore, always keep your capacitors close as possible to these pins, input and output capacitors, in order to get the maximum performance, and also these resistors, feedback resistors, close to these pads. That is some layout tips when you're designing PCBs using linear regulators. I hope this lecture will give you some insight and more knowledge on you for your design, power supply design. Right, now we can do an example. We are going to build and test a adjustable linear regulator in simulation. Before we move into this exercise, if you have any questions, you can ask them now. Okay, looks like no one has questions, so I will just simply show you how to do this one. So we have this linear regulator. Let me show you the. Can everyone see the PDF? Okay, right. So this is the linear regulator that we are going to test. It's a high PSR low dropout regulator, and we are going to build the 3.3 volt regulator using this one. It's an adjustable one. So by changing the resistors, feedback resistors, we're going to get 3.3 output. The input voltage range could be from here to here, but we are interested in maximum value. And this one could be used for automotive head units for lighting. So I have sent you to look at these things. So this one has 5 pins. The first one is enable pin. So you have to drive this pin to logic high in order to enable the LDO, otherwise it won't work. If you put into the ground, no matter, it will not provide the output regulator. So if you want to enable this, you have to pull this to the V in supply voltage. Always make sure this is either connected to the ground or connected to the supply. If you want to run it, you have to connect it to supply. But if you want to externally control it using a microcontroller or any control circuit, you can connect to a digital pin, and whenever you want to run the LDO, you can just make this pin high. That's the use of enable pin. And feedback pins are to connect to your resistors, ground pin, and in is your supply voltage. And NC means it is not connected to anyone, so you can just left it floating. This is output pin is where you take your output load, and thermal pad is for heat sinking. This one should be connected to a copper port to release the heat dissipation of the internal series pass device, so you can keep your device within a safe temperature range. So these are the absolute maximum rating. So you should not increase your supply over than 6.5, otherwise the device will fail. You have to keep your heat sinking in the desired level and to keep this internal die temperature less than 150 degrees. Yeah, these are the very essential things. And recommended conditions. So your input capacitor should be within this range. Typical 1 microfarad capacitor will be suitable, and output capacitor could be range from 1 microfarad to 200 microfarad. And the ESR, this is the interesting one. So in order to run it in a stable manner, it should be 1 milliohm to 1 ohms of resistance. You have to keep this ESR within this value to make your LDO regulator working without an issue. And these are the ranges. So supply voltage, typical range, you have to keep it 6 volt or less than 6 volt. Output voltage and the accuracy and line regulation, as I mentioned, is very low, 3.3 millivolt drop. And load regulation is also very low, 50 millivolt drop based on your changes in the load. And the ground pin current, that is due to the consumption of the control blocks, is very low, microamps range. Shutdown current is when you disable the enable pin, is sort of the quiescent current drops even below than these values, right? This is in running mode, and this is in shutdown or the standby mode. That is very low. It is really essential when you are using this one for save your battery life. And feedback voltage, feedback currents are important when you're calculating your feedback resistors. And it has a short circuit protection. If suddenly someone short circuit the output, it will limit the output current in order to safeguard the LDO. So the dropout voltage is typically 315 millivolts. That is the drop across your series pass device. That is a very low value, right? Which means you can run your LDO to a very high efficiency. And This is the line transient response, which means you can change your supply voltage to increase that. So this is how the output voltage changes. So initially it will drop and it will settle down to the desired level, and when you reduce the supply voltage also, it will increase initially and settle down to the desired level. And finally, we have this power supply ripple rejection characteristic. So you have to be looking at if you want to get rid of noise coming from your power source. So at low frequencies, the PSR is around 70 to 80 decibel. And when the frequency increases at 10 megahertz, the PSR is drops to 20 decibel. And this is the tunnel of death characteristic, that is the ESR range. So here they have plotted this output capacitance against the ESR. So if you pick 10 microfarad capacitance, this should be your ESR range, right? If you select 200 microfarad capacitance, this should be your ESR for stability, right? So you have to look all these parameters when you're designing a regulator, and this is how it is internally looks like. We have the series pass device, error amplifier, and reference voltage source. This is your feedback signal comes here, and this has an internal control circuit, and this is for I think overcurrent prevention. And this fallback current limit is when there's a short circuit event or overload event happens. So you might have seen in your benchtop power supplies, if you short circuit, the voltage drops to a very low value. Same thing happens here. So that will safeguard your output load and the power supply. Thermal shutdown is if it is consuming more heat and more heat internally. So if it is reaching a threshold value, the LDO regulator will shut down by itself to prevent getting it damaged. So those features are additional features comes with the linear regulator. So they have recommended this kind of output capacitors. Ceramic output capacitors are recommended, and the capacitor should not decrease more than 50%. And this is the temperature coefficient that I was talking about, like X7R is very good temperature coefficient, which means the capacitance and ESR does not change much due to the variation of the outside temperature. Right. So this is the typical application when you making a LDO regulator to, for example, for your Arduino project or anything, automotive application. So you have to, this is a 5-pin device. So enable this, either you can connect it to a control circuit, or either you can simply fold it out to the ins if you don't want to control and if you always want to run it. So you can just connect it to here. And this is your input capacitor. And this is your output capacitor. This feed port capacitors are for noise filtering, but we are not using this. And you have to use your feedback resistors in this way. And in order to get this output voltage to our desired value, that is 3.3 volt. So this is the regulator that we are going to use. And so you have to calculate the value of R1. So that is this example is about calculate the value of R1, satisfy this equation. So in order to make this circuit to generate 3.3 volt output. So you have to use this equation. VFP and IFP values are given in here. You can substitute them from this table. See, the VFP feedback voltage could range from here to here, but you can just use this typical value, that is 1.2. And IFP value is 0.01 microampere. Substitute that value here. And assuming R2 as 100 100K, you can take R2 as 100K. Then you can find the value of R2 to provide 3.3 volt output. So quickly find that value that requires to get the 3.3 output. So after that, we can discuss this one. So by using these values, can anyone find the value for R1 before we build this one in the simulation? You have to find the value of R1. Take R2 as 10K and substitute in this equation. Your desired output voltage is 3.3 volts. And type the value of R1 in the chat box. Okay, if you correctly got this value, it should be around 175 kilo ohms. And you have to pick your input and output capacitors as specified by the datasheet. I have shown you these values. And the ESR also by referring to the datasheet. And this is how you're going to build it in the Tina Spice. I have yesterday shared with you this this IC, and this is how you connect the in pin to the supply and your input capacitance. I have used 10 microfarad with 100 milliohm ESR. The input capacitor doesn't matter, the ESR. And the output capacitor, I have selected 10 micro with 100 milliohm ESR. And this is how I have connected my feedback resistors. And in order to get the 1 amps current, I have put 3.3 ohm resistor. And this is, I have connected test probes at V in, V out, and I out. So you have to design this in Tina and simulate and get the no load voltage, output voltage, and full load output voltage. And by changing the input voltage, this battery voltage, you have to fill this table. Find the input current, output voltage, output current, input power, output power, and efficiency for these ranges. So you can simulate for several times and get these results. And find the line regulation at maximum load current, which means from this data, the line regulation is plot the supply voltage in x-axis and the output voltage in the y-axis. Then you can get the line regulation. So this is your V in and this is your V out. You can plot it. Then you can at maximum load current 1 amps current. So you can determine what is the slope and find the line regulation. Efficiency, you can again plot the efficiency from here, get these values and plot it against the input supply. So you will see this how the efficiency changes with the supply voltage. In order to get the load regulations, you have to change your load current, change the resistance for different load currents and find the output voltage and then plot it. This is your I out and this is your V out, and plot it by keeping V input voltage fixed. Sorry, this should be fixed to a value around, let's say, should be corrected to 4.5 volts. By keeping the supply voltage at 5 volts, change the output current and find the output voltage and then plot the V out and V out and I out. So you can find this from the slope, you can find this line regulation. In order to get the PSR, so you have to provide 10 millivolt signal at 1 megahertz range. So use this signal generator and set its values to like this. And you can observe the output voltage using the oscilloscope and measure the amount of output voltage, and then using the PSR equation, determine the PSR at the output. So you need to use the oscilloscope to at the output to get this output voltage. To get the transient response, so you have to change your load, reduce the load by 50%. So I have connected 6.6 ohm resistor to in series. So it's running at 50%, or just running at full load. Initially, the switch is closed, which means it's running at full current. And when it is this control signal from this function generator goes to high, which means it's a NOT gate. So it open the switch, which means the load drops to 50%. From that, you can observe how this output voltage changes. So your load is reduced from 50%, 1 amp to 500 milliamps. And your output voltage should go like this and go like that. So you have to observe that by using this setup. Finally, overloading. So you have to just short circuit the output and see what will happen to the output voltage. So it has internal overload shutdown. So you will see how it works. Right, that's all about this simulation example. Pretty much easy. If you have any questions, you can ask it now, or you can build this circuit in your TINA Spice simulator and get the results and work this by yourself. That will help you to study more about the linear regulators and circuit simulations. So any questions? Anyone has questions? So otherwise we can wind up the session. Looks like everything is clear, crystal clear, and so I hope everyone will get a chance to work on this circuit and get the results, and using your lecture notes and fill these tables and work on these examples. And so that will be all about linear regulators. Next week we will discuss other types of voltage regulators. Can enable pin be used to switching to get the adjustable voltage? No, it is not a switch mode power supply. If you want to shut down, for example, if you want to save the power, for example, if you have a mobile phone, when your mobile phone at standby mode, so when you're not using, you just put on your table, so you don't need to use your display or any other thing, right? So internal control circuit will detect as your mobile phone is not operating, use is no longer used, so you will just pull this enable down. That means so the output is disabled, only the quiescent current, standby quiescent current goes down, so that will save the battery life of the supply. So if the user get the phone to his hand and just turn on the device display, so then the control circuit detects it and enable the regulator that will provide the power to your display like that. So that's the purpose of having enable pin. It's not like a switch mode power supply. Either you just pull it up high to enable the output and pull it down to disable the output. When you disable it, it will go to the standby mode. That will draw very low quiescent current compared to the nominal operation. So which means you can save your battery life. Okay, then no one has questions. So we'll wind up the session. So we'll meet you next week.